So our goal in this lecture is going to be to develop a heuristic definition, that is a list of properties that we can use to identify functions that are continuous or that are discontinuous. Now, of the four graphs here, we only want the first one to qualify as continuous. It has no gaps or breaks, and we could start at one end and sketch the entire graph without ever picking up our pencil. Now, the other three, on the other hand, all have problems at x equals 1, here, here, and here, that are going to disqualify them. So the definition we come up with needs to take each of these cases into account. It's going to need to disqualify each of these cases. So the first part of our definition says that for a function to be continuous at a specific point, it first has to exist at that point. Right, so let's go to our graphs and see how this applies to each of them. Well, the first graph is defined at x equals 1. So far it qualifies as continuous, which is what we wanted for this graph. Now, the second graph, however, does not exist here at x equals 1. So it fails this test. This means that using our definition so far, this function is not continuous at x equals 1, which is what we wanted to happen. Now, the third and fourth graphs are defined at x equals 1. Both graphs, well, the first graph equals 2 there, and the second graph equals 3. So again, based on our definition so far, these functions would qualify as continuous, which we don't want. So we're not done. We need to keep expanding on our definition. Our second requirement for a function to be continuous at a point is that the limit as x approaches that point has to exist. Okay, so let's go back to our functions again. As x approaches 1, the first function here approaches 0 from each side. So this function is both defined at x equals 1 and the limit as x approaches 1 exists, which is good. Even with our new criterion, this function is still continuous, which is the result that we want. So the second graph, we don't have to worry about it. It's still discontinuous based on criterion 1. Now, looking at the second graph, the limit as x approaches 1 from the left is 1, where the limit as x approaches 1 from the right is 2. Okay, so because the left and right limits are different, the overall limit doesn't exist, which means this function fails our second criterion. That makes it discontinuous at x equals 1, which is what we wanted for our definition to do. Okay, so now for the third function, the limit as x approaches 1 from the left, and the limit as x approaches 1 from the right, are both equal. They both equal 0. So this means that the limit as x approaches 1 exists and equals 0. So this means that using the definition as we have it so far, right, with just these two criterion, this function is still coming out as continuous. So one more requirement will give us the definition that we need here. Right, our last requirement is that not only does the limit have to exist, but it has to actually equal the value of the function at that specific x value. So graphs 2 and 3 here, we've already ruled out. This one based on not meeting criterion 1, and this one based on not meeting criterion 2. All right, so for graph 1, up here, f of 1 does equal 0. So the limit as x approaches 1 does equal f of 1, which is good. This function, we want it to be continuous, and it meets all three of our requirements. All right, now remember for graph 4 down here, we had the limit as x approaches 1 of f of x equals 0. All right, but we can see this point right here, f of 1 equals 4. This means that the limit as x approaches 1 does not equal f of 1. So finally, this graph fails this last criterion, so it is also discontinuous at x equals 1. All right, so now that we have our definition, right, let's take a step back and think about what it means. In practice, if you want to determine if a function is continuous at a point, you have to check that it meets all three of these criteria. If just one of them isn't true for your function, then the function isn't continuous at that point. Or, looking at it from the other direction, for a function to be continuous at a point, all three of our criteria have to be true for the function. Okay, so finally here we have one last extension of our definition. If a function is continuous at every point in an open interval, then we say that it's continuous on the whole interval. So this definition, it just extends our previous definition from individual points to an entire range of values. So to see how this can be applied, take a look at one of our problem functions here. Remember that the only problem point, if you will, was x equals 1. So that means that we could say that the function is continuous on the interval from 2 to 4 because there aren't any problem points. The one point where the function is discontinuous isn't in that interval. On the other hand, we could not say, for example, that the function is continuous on the interval from 0 to 2 because there is this point in that interval where the function is not continuous. All right, so in the following lectures, we'll look at some specific examples of how to determine, when a function is continuous or discontinuous at a specific point.